Have you ever had one of those aha moments, a great idea, and just thought, man, I wish a computer could do this for me? Well, that's really what programming is all about. It's the art of taking our human ideas and turning them into a set of super precise instructions a machine can actually follow. So let's dive right in and see how that happens. It kind of sounds like a riddle, right? But it actually gets to the very heart of what computing is. You see, the silicon in a computer chip is, well, it's essentially purified sand, a rock. And programming is this incredible process of giving that inert piece of silicon instructions so detailed, so precise, that it can perform ridiculously complex tasks. So yeah, when we program, we are, in a very real sense, teaching rocks how to think.
You know, a great way to think about programming is to see it as a bridge. On one side, you have us, with our intentions and our logic. On the other side, you've got the raw, binary world of the machine. Programming is that translation layer, that bridge that connects the two. It's how we tell the hardware what we want it to do.
To really understand how this bridge gets built, we're going to follow what I like to call the programmer's journey. We're going to take one super simple problem and watch how it goes from just a basic concept into a real, working, and, this is key, an efficient program.
You know, every programmer, it doesn't matter if they're building a simple web page or, a guidance system for a rocket, they all follow these 4 fundamental stages. So this is going to be our roadmap. First, we design, then we code, after that, we test, and finally, we make sure it's all running with top-notch efficiency.
All right, let's kick things off with stage 1, design. Now listen, before you even think about writing a single line of code, you have to really, truly understand the problem. What information are you starting with? That's your input. And what do you need to end up with? That's your output. For our little example here, the input is just a bunch of numbers, n of them, and the output is their total sum. Sounds simple, but getting this right is absolutely critical.
See, a good programmer never tries to solve the whole thing at once. They use a divide and conquer strategy. For our sum problem, we can easily break it into 3 clear parts. First, we need a way to get the numbers. Second, we do the actual calculation of the sum. And third, we display that final result. Easy, manageable chunks.
Now we get to the core logic. We create an algorithm, which honestly is just a fancy word for a recipe. And our recipe here is pretty straightforward. Start our sum at 0. Get the list of numbers, and then, one by one, add each number to our running total. Once you've gone through all the numbers, just show the final sum. The key here is there's no ambiguity, just clear, repeatable steps.
So our recipe says repeat n times. But how do we tell a computer to do that? Well, that's where tools called control structures come in. For a repetitive job like adding up a list of numbers, an iteration tool, something like a for loop or a while loop, is the perfect choice. It tells the computer exactly how to execute that repetition.
And here it is. This is the magic moment. With our design complete, our whole plan laid out, we move to stage 2, coding. We take our abstract recipe and we translate it into a specific programming language. In this case, you're seeing our algorithm written out in C, all ready for the machine to execute.
But writing the code, that is rarely the end of the story. In fact, a lot of the time, it's just the beginning of a whole new challenge. Every single programmer will tell you that mistakes, or as we call them, bugs, are just an inevitable part of the process.
And these bugs, they usually come in 3 main flavors. First, you've got syntax errors, which are basically just grammar mistakes, like a missing semicolon. Then there are runtime errors. These are problems that make the program just crash while it's running, like trying to divide by 0. And finally, the trickiest of them all, logical errors. This is where the program runs perfectly fine, no crashes, but it gives you the wrong answer because your recipe, your logic, was flawed from the start.
Okay, so you've hunted down and fixed all your bugs. Your code runs, it gives the right answer every time. Mission accomplished, right? We can go home? Well, not quite. Now we have to ask an even deeper question. Is our solution efficient? And that brings us to the final stage.
You see, program efficiency isn't just about how fast a program runs on your computer right now. It's really about how its performance scales. We measure this in 2 main ways: time complexity, how many operations it takes, and space complexity, how much memory it uses as the amount of input data gets bigger and bigger and bigger.
And this right here is why your choice of algorithm is so important. Just look at how quickly things can spiral out of control. For an input of 1,000 numbers, a good linear algorithm takes about 1,000 steps. Makes sense. A slightly worse, quadratic one takes 1,000,000 steps. And a really bad exponential one, The number of operations it's larger than the estimated number of atoms in the entire known universe. That's not just slow, it's literally impossible to compute.
This graph really says it all. The goal for any programmer is to stay in that nice, predictable green zone. We want solutions where the cost grows slowly. That red zone, that represents catastrophic failure, algorithms that become totally useless with even a moderate amount of data. Trust me, an inefficient algorithm on the world's fastest supercomputer will always be slower than an efficient one running on your phone.
Okay, so we've followed one problem all the way through the 4 stages. Now let's kind of zoom out and take a look at the toolbox that programmers get to use. The choice of programming language is huge, and these tools have evolved like crazy over the years.
In the very beginning, programmers literally had to speak the machine's native tongue, raw binary, just ones and zeros. That was the first generation. The second gen, assembly, gave us simple keywords which made it a little more human-readable. Then the third generation brought us high-level languages like C and Fortran, which let us write much more complex logic. And today, we often use fourth-generation object-oriented languages like Python and Java that let us model real-world things right inside our code.
And if we're going to talk about foundational tools, well, there is one language that we absolutely have to talk about. One of the most important ever created, C.
C was created way back in 1972 by the legendary Dennis Ritchie. And it wasn't just another language, it was the specific tool built to create the Unix operating system. From its early days with the famous KNR book setting the standard, all the way to its latest official update in 2023, C has been constantly evolving for over 50 years.
So, what makes C so powerful? Well, it's all about its unique balance. First, it's what we call a mid-level language. It bridges that gap between our human logic and the machine's actual hardware. And because it's so close to the hardware, it is incredibly fast and efficient. It's also super portable, meaning code written on one computer can usually be compiled to run almost anywhere. And maybe most importantly, it's a foundational language. If you learn C, you've built a strong base for understanding so many other modern languages. But here's the thing. As powerful as C is, it's not a silver bullet for every problem. A really crucial skill for any modern programmer is knowing when to use a specific tool and when to choose something else from the toolbox.
The takeaway here is pretty simple. You use C where speed and direct control over the hardware are the most important things. Think operating systems, game engines, or the tiny little computer running inside your microwave. But for things like web applications, data science, or huge business software, other languages like Python and Java often give you more built-in safety nets and features that make them a much more practical choice for those specific jobs.
And there you have it. We've gone from a simple idea to an analysis to an algorithm to code that's been tested, debugged, and made efficient. We've even seen how the tools for this job have evolved over time. At its heart, programming is a creative act of solving problems. So the only real question left is, what problem will you teach a machine to solve next?